let's do the first problem on the second relativity lab. In this, which we discussed in class, we have Newton standing next to his Newtonian blades of death, and we have Einstein flying along in this direction. And the Newtonian blades of death are separated by 1 meter, and Einstein, in his frame, is 2 meters long. And the question is, first question is, how fast does Einstein have to go in order to not get chopped by the Newtonian blades of death? Well, remember that objects that are moving have their lengths contracted. So that formula is that the length that an observer will perceive the moving object to be is equal to the proper length divided by this factor gamma. But remember that the proper length is the length of the object in a frame where it's not moving. So Einstein's proper length is 2 meters, because that's how tall he is in a frame where he's not moving. In a frame where he is moving, his length will be shorter. So how short does he need to be to not get chopped by the blades of death? Well, if the blades of death are 1 meter apart, Einstein can be at most 1 meter tall in that frame to avoid being chopped into pieces by the Newtonian blades of death. So if we say that the length we want him to be is 1 meter, and his proper length is 2 meters, then that gives us that the gamma factor is 2. So we need gamma equal to 2 for him to be short enough to survive. So gamma equal to 2, well, remember gamma is 1 over square root of 1 minus b squared over c squared. So if this is equal to 2, then we can solve this pretty simply and get that v is equal to square root of 3 over 2 times c. That's how fast he has to be to have a gamma factor of 2 to be compressed by a factor of 2, so he's only a meter tall. So in Newton's frame, Einstein moves this fast. He's shrunk to be only 1 meter tall. He fits right between the blades of death. The blades come down on either side of him. So they come down here and here. He fits right between them, and then he flies on to safety. So he lives. What does he see in his frame of reference? Well, in his frame of reference, let's keep that v is equal to square root of 3 over 2 and that gamma is equal to 2 here. In Einstein's frame of reference, he's 2 meters tall, and you have the Newtonian blades of death, with Newton standing next to them. And these things are flying towards Einstein. So in his frame of reference, he's just sitting there, or lying there, watching these blades come towards him. And what's going to happen that's going to cause him to live? Well, since the 2 blades are moving relative to him, they are not going to be 1 meter apart, their length is going to be contracted. So the length that they're normally separated is by 1 meter, but he'll perceive them contracted by the same gamma factor. If the blades see Einstein moving at square root of 3 over 2c, then Einstein sees the blades moving at square root of 3 over 2c. So the gamma factors are the same, so the blades of death are only a ½ meter apart. But he's 2 meters long, which means that there's nowhere to put these blades where if they go down simultaneously, he will survive. So how does he survive? Well, to do this, let's use the Lorentz transformation equations to find out how he perceives things to be. So let's say that we have 2 events. We have blade A and blade B. So we're going to have event A, which is the blade A dropping, and event B, which is blade B dropping. So we have Newton observing this, and we have Einstein observing this. Newton says that event A happens at time 0 and at location 0. So it happens right where he is at time 0. Newton says blade B drops at the same time, but 1 meter away. So now we need to find out what Einstein says these things do. Well, to solve that, I'm going to require you to remember these things here. I'll write them over here. To solve these, we have to use the Lorentz transformation equations. So what do these equations mean? What these equations mean is that one observer measures an event that happens at a location t, at a time t and location x. You want to know what time and space the other observer perceives that event to happen. So Newton measures a particular t and a particular x. This will then tell us what the t prime that Einstein sees and x prime that Einstein sees is. So let's take these two events and put them in. So Einstein will perceive event A, gamma is 2, time is 0 for Newton, space is 0 for Newton, so the x-coordinate is 0. So 0 minus 0 is 0 for time. And similarly for x prime, the gamma factor is 2, the location is 0, the velocity is square root of 3 over 2 times c, and the time is 0. So the space is 0 as well. So Einstein also says that event A happens at 0, 0. What about event B? Event B for Newton happens at a time 0, but an x-coordinate 1. So Einstein, gamma is 2, time is 0, velocity is square root of 3 over 2 times c, and x is 1 meter. So the time that Einstein sees this event happen at is minus square root of 3 meters divided by c. What about the space coordinate? Gamma is 2, x is 1, velocity is square root of 3 over 2 times c, and t is 0. So the second piece is 0, so Einstein measures the x prime to be 2 meters. So Einstein says the second event happens at minus square root of 3 meters over c at a location of 2 meters. So what does that mean he sees? He sees these blades coming across. When the blade B gets to his head, it drops. It drops first at a time minus square root of 3 meters over c. Then the blades continue to move, and then blade A drops at time 0. So for Newton, these two blades fall simultaneously, but miss Einstein because he's contracted. For Einstein, who does not perceive himself to be contracted, the blades miss him, but they miss him because one of them drops first, then they move, then the second one drops, and they continue on, and he lives quite happily. Lastly, we can calculate the invariant spacetime interval between these two events. Remember what the invariant spacetime interval is. The invariant spacetime interval is a useful quantity because it's something that everybody agrees on. So you might measure a different time from somebody else, you might measure a different space from somebody else, but you all agree on the invariant spacetime interval. So what do? Ignoring x and y for the moment, just thinking about time and x. Sorry, ignoring y and z for the moment, just thinking about time and x. This is our invariant spacetime interval. So delta t is the time of the second event minus the time of the first event, and delta x is the location of the second event minus the location of the first event. So for Newton, the times are the same. So for Newton, the separation in time is 0. The separation in space for Newton is 1 here and 0 there. So that's 1 minus 0 is equal to 1. So for Newton, delta S is equal to c squared times 0 minus 1 meter squared. What about for Einstein? Well, for Einstein, one event happens at minus square root of 3 over 2, and one happens at 0. So delta t is minus square root of 3 m over c. And delta x is 2. So when I now plug into this formula, what do I get? I get c squared times minus square root of 3m over c squared minus 2 meters squared. Square root of 3 squared is 3, c squared over c squared. So this whole thing is 3 meters squared minus 4 meters squared is equal to minus 1 meter squared. That's exactly what we got for Newton. So this is a check. We did our coordinate transformation. We started with Newton's coordinates for the two events. We then found Einstein's coordinates for those two events. We calculate the space-time interval between them for Newton. We calculate the space-time interval for them for Einstein. We get the same answer, as we should, because the one thing that all observers agree on is the invariant space-time interval between two events.